So let's discuss calculation of Clebsch Gordan coefficient for J1 equals to 1 and J2 equals to half. So this is nothing but that is for p state of an electron they are saying. So because for p state of an electron we have L value equals to 1. For S we have uh, azimuthal quantum number 0 and for P we have azimuthal quantum number 1. So here J1 can be considered as orbital quantum number, that is azimuthal quantum number 1, and J2 is spin. J2 is equals to half. So for if the electron is residing in pth orbital, then its L value would be 1. And because of if it possesses spin, it could be plus half or minus half, like that. So hence this case can be considered as for the p state of an electron. So when J1 equals to 1 and J2 equals to half, could be considered taken under p state of an electron. So the p state of an electron is characterized by orbital quantum numbers J1 equals L equals to 1 and spin quantum number J2 equals to S equals half. So as said now. So obviously the possible values of magnetic quantum number for J1 equals L equals 1 are, so for a given L value, as we know, we have 2L plus 1 possible M values. So as here L is 1, 2 into 1 plus 1, that is 2 plus 1, that is 3. So we are having 3 possible M values and they are lying from minus L to plus L with a difference of 1 unit. So difference between each of the values. So minus L, as L is 1, so minus 1 to plus 1, and minus 1 plus 1 is 0, 0 plus 1 is 1. So and those for J2 equals to S equals to half or M2 is equals to plus half minus half. So for S is equals to half, we have plus S to minus S. So here plus S is nothing but half and minus S is nothing but minus half. And we know that half minus 1 is nothing but minus half. So we won't have 0. So the interval should be 1. Equal intervals, that is 1, and difference between the two values must be 1. So half minus 1 is nothing but minus half. So minus S to plus S. So only two possible values, because 2S plus 1 is nothing but 2 into half is nothing but 1. 1 plus 1 is nothing but 2. Only two possible values we are having based on that formula. So the possible values of total angular momentum quantum number J associated with J capital J is. So now we have to consider the possible values for the total angular momentum. So the possible values of total angular momentum quantum number. So if we consider overall total, if we consider not J1 separately and J2 separately, if we add up, so totally if we consider, we have J is equals to L plus S. So in the place of L here we are having 1, in the place of S we are having half. So 1 plus half is nothing but 3 by 2 and L minus S. This is also the possible case. So my L minus S to L plus S we are having. The possible values of J are nothing but smallest possible value of J is L minus S and maximum possible value of J is L plus S. So 1 minus half is nothing but half. So half plus 1 is nothing but 3 by 2 and 3 by 2 minus half, 1 is nothing but half. So with an interval of 1. So only the possible values of total angular momentum are L plus S, that is 3 by 2, and L minus S, that is half in this case. So these are all the possible values of total angular momentum. And now we need to consider separately the values of magnetic quantum number for these J values. So as M varies from minus J to plus J, the possible values of M for J equals 3 by 2 are, so minus J2 plus J, and here in the place of J we are having 3 by 2. So 2 into 3 by 2 is 3 plus 1 is 4. So we would have 4 possible M values. They are minus J2 plus J, that is minus 3 by 2 to plus 3 by 2 with an interval of 1. So minus 3 by 2 plus 1 minus half plus 1, 1 by 2, 1 by 2 plus 1, 3 by 2, like that. And those for J equals to half are half and minus half. So minus J2 plus J with an internal of 1. So we are having half and minus half. So the possible set of eigenfunctions in uncoupled representation is psi of m1 comma m2. So the possible in uncoupled form, that means m1's one separately, two separately. If we consider these two separately, m1 and m2 separately, if we consider, so uncoupled representation, we are having these many xi values, that is xi is equal xi of 1 comma half. As we already know, we have already found out m1 possible values of m1 are 1 0 minus 1, and those of m2 are half comma minus half. So we have to consider the possible combinations. So here we are having three values for this, here we are having two values for this, so 3 2s are 6, so there would be 6 possible combinations. So when m1 is equals to 1, so m1 is equals to 1, these are the two possible values, and m2 is plus half minus half. And when m1 is equals to 0 0 0, and m2 is plus half minus half. And when m1 is minus 1 and m2 having plus half minus half. So overall we would have 6 possible combinations, 6 possibilities. The possible set of eigenfunctions in coupled representation. So this is in uncoupled form. So m1 separately, m2 separately. So once they are coupled, once we form total angular momentum, so in that case phi of j comma m is nothing but, so we have already found here coupled form, that is j values, m values for the coupled form. So we have one of j values 3 by 2, and its possible m values are this 4. So 3 by 2, 3 by 2, 3 by 2, and possible m values 3 by 2, half, minus 3 by 2. So for a given j, 4 possible. For a given j 3 by 2, we have 4 possible m values. 3 by 2, 3 by 2, 3 by 2 half, 3 by 2 minus half, 3 by 2 minus 3 by 2. And for a given j value half, we have 2 possible m values, half comma minus half. So this is that j value half, and its possible m values half comma minus half. So for this also we are having 6 possible combinations for the coupled representation also, eigenfunctions for the coupled representation. Now the transformation equation representing the wave functions of coupled representation in terms of wave functions of uncoupled representation is, so this is the coupled form. So what we are doing here, what is getting is transformed is here uncoupled form. This is uncoupled wave function, it is being getting transformed to coupled form. So uncoupled form means we are having m1 comma m2, and uncoupled form means we are having m1 comma m2, uncoupled form is j comma m. So this type of wave functions are getting converted to this, transformed to this kind of wave function. So this is the transformation equation. How we are getting transformed is with the help of this multiplying with these coefficients. These are nothing but Clebsch Gordan coefficients. These are the coefficients we needed to find now. So if we multiply these possible uncoupled wave functions with this corresponding Clebsch Gordan coefficients and add up, we would get the corresponding coupled form. So that is the meaning of this equation. So phi of j comma m is equals to summation m1 comma m2, and here this is nothing but bra m1 comma m2 jm get xi of m1 comma m2. So this form is getting transformed to this form. So m1 comma m2 form is being transformed to j comma m form, that is m1 comma m2 uncoupled form is being transformed to coupled j comma m form. So that is the equation. So operating by jz equals to, so here jz is nothing but j1z plus j2z, because we are having j1 comma j2. Because of that, jz and written as j1z plus j2z, or lz sz also we can write. So jz, so for this equation we are operating on both sides with this jz. So operating jz getting operator on this. So as this is coupled form, jz will remain the same, and this is uncoupled form. So here we are separating it, j1z plus j2z getting operator on this wave function. And we know that Jz is an operator operating on wave function, giving the same wave function multiplied with its eigenvalue. So the eigenvalue for Jz is mh cut. So if we take h cut has one unit, then in the place of mh cut we would have m. So Jz operating on wave function phi of j comma m is giving the same wave function with its eigenvalue mh cut. So h cut is 1, so m. And here also the same. So here J1Z would operate only on M1. J1Z would operate and it would give M1 H cut. So hence M1. And here J2Z would operate on this wave function. It would give M2 H cut. So hence we are having M1 plus M2. In the place of H cut we are having 1. So for J1Z eigenvalue is M1 H cut. For J2Z eigenvalue is M2 H cut. So after this being operating on this wave function, it would give the same wave function multiplied with its eigenvalue. Based on the eigenvalue equations, we are having this equation after operating, and using equation 1 we get. So now from equation 1 we have phi of j comma m as this. So in the place of phi of j comma m we need to substitute this entire thing. This summation and psi has to be substituted in phi of j comma m. So if we substitute, what would happen is, here also summation this Clebsch Gordan coefficient xi we are having, and here after substitution also here summation this Clebsch Gordan coefficient xi would be there. So that would be taken as common, and we need to send this term to that side. So if we send that side, this could be taken as common, this both terms. So what would remain is m1 plus m2 minus m, because this is common for both, and here m1 plus m2 is there, here m is there. So that one would go to that side, we would have minus m. So this is equal to 0. And next thing is, as xi of m1 comma m2 are linearly independent functions, therefore we have m1 plus m2 minus m into m1 m2 bra of m1 m2 jm get equals to 0. So actually this is of the form, the equation was of the form this ax plus by plus cz equals to 0. So as here x, if we consider x, y, z are all independent, they do not depend on each other, then this is possible only when a, b, c equals to 0. Their summation would become 0 only when a, b, c, their coefficients are 0. And if they are dependent, if we suppose y is equals to 4x, z is equals to some 3x like that, then we would have some possible values for one a, b, c, that is minus 1, minus 2, minus 3, or plus 1, 2, 3 like that. So in order to get finally 0 after multiplication. But here if x, y, z, we cannot write y has 4x, if we cannot write z has 3x, we cannot express one thing as the other. They are not dependent on each other, they are not linearly dependent. So this is nothing but linear dependency. If y is equals to 4x, if they are not linearly dependent, means this case would be possible only when a, b, c, their coefficients are separately 0. So that is the thing. Hence here also, as these wave functions are all independent, this summation would become equal to 0 only when its coefficients are 0. So this is the coefficients of this wave function. So this coefficient must be equal to 0. And another thing is, this is of the form ab equals to 0. So then we would have either a equals to 0 or b equals to 0. So either this term equals to 0 or else this term equals to 0. So if this term equals to 0, we would have, sending this m to that side, m is equals to m1 plus m2. So important conclusion from here is, so when m is equals to m1 plus m2, we would have Clebsch Gordan coefficient is not equal to 0. That means we would have non-vanishing Clebsch Gordan coefficient. Finally we can see that. And when this term is m is not equal to m1 plus m2, then those Clebsch Gordan coefficient would definitely vanish based on this condition. So in that case we would have Clebsch Gordan vanishing Clebsch Gordan coefficients. So this would be discussed at the end of this section. And next thing we have is the numbers j1 and j2 are largest values of m1 and m2 respectively, and largest possible value of m is equals to m1 plus m2 j1 plus j2. So here j1 and j2 are the largest possible values of m1. So just like if L value is 2, then the maximum possible value of m is 2. And if L value is 3, maximum possible M value is plus 3, like that. So the numbers J1 and J2 are largest possible values of M1 and M2, and as we know M is equals to M1 plus M2, its largest possible value would be J1 plus J2. In place of M1 we need to replace it with J1 and M2 by J2. So what we would have is, then equation 1 reduces to single term. So in equation 1 what we are having, this is equation 1. So in the place of j, j1 plus j2. In the place of m also j1 plus j2. Because j is consider maximum possible value if we consider. So j1 plus j2, and m here we have considered in the place of m, m1 j1, and in the place of m2 j2. So this is the thing. And here again what we are having, m1 m2 summation. So here m1 m2 jm is there. So here in the place of m1 j1, in the place of m2 j2, and here next jm is there, and here also j1 plus j1 plus j2, and xi of m1 comma m2 is there. Xi of m1 comma m2. So xi of j1 comma j2. So we would get only one Clebsch Gordan coefficient, because there would be only one possible m1 plus m2. So when m is equals to m1 plus m2, then only we would have Clebsch Gordan coefficient. So that is only for this case. So this is that case. When m1 is equals to j1 and m2 is equals to j2, this is the possible case. And in that case we would have m is equals to m1 plus m2. So this is the possible equation. And using normalization condition we obtain. So we know that normalization condition is nothing but integration of xi star d tau is equals to 1. In the same way, integration of phi star d tau is equals to 1 we have. So on the right hand side also, integration of this term multiplied with xi star and its conjugate term, conjugate of this bracket, we would have integration of xi star d tau equals to 1. On the left hand side also, integration of phi star d tau is equals to 1, and what would remain is this term and its complex conjugate, both multiplied together. We would have this modulus of this whole square equals to 1, because a complex number multiplied with its complex conjugate gives us the modulus of that particular complex number, magnitude of that complex number whole squared. So based on that condition we would have this term, this equation, and sending this square to that side, that is nothing but square root of 1, we would have this term. So this is nothing but equal to 1. Based on the property of complex numbers, we are having this term. Complex number multiplied with its complex conjugate gives us magnitude of that complex number whole square. So just like if a plus ib is a complex number, its complex conjugate is a minus ib. If we multiply this both, so you would have a square minus ib whole square, that is I square is minus 1 minus into minus plus b square. So modulus of this complex number is nothing but square root of a square plus b square, that is its magnitude. Whole square is nothing but a square plus b square. So based on this property. So here we need to neglect phase factor, that is e power I theta, like that we would be having. So we are just neglecting this phase factor. So if we neglect that, we would have this entire term equals to 1. And thus equation 3 reduces to. So this equation, this is the equation. So as we have found this term, this bra j1 j2 j1 plus j2 get equals to 1. If we substitute here, this equation would become this. In the place of this term we would have 1. So this is the equation. And in the question it is already given that j1 is equals to 1 and j2 is equals to half. So we just need to substitute here. So 1 plus half is nothing but 3 by 2. Again 1 plus half is nothing but 3 by 2. And 1 j1 is nothing but 1, j2 is half. So this is the required equation. And this get, so 1 half bra of 1 half, and this in the ket we are having 1 plus half, that is 3 by 2, 1 plus half 3 by 2 equals to 1. So based on this two equations, if we substitute these values, we would have these two equations. So this is one of the important Clebsch Gordan coefficients. So we have found out one of the Clebsch Gordan coefficients. Now next thing is operating equation 6 by j minus, that is equals to j1 minus plus j2 minus, where the eigenvalue of j minus is root over j plus m into j minus m plus 1, and it reduces the value of m by 1 we get. So next thing what we have to do is, we are starting from maximum possible values. That's why we have taken m1 is equals to j1, m2 is equals to j2. Now we can operate it with j minus, because it just keeps on reducing the value of m by 1. So here, that is the thing here, it is mentioned, reduces the value of m by 1. So it would keep on reducing. If we operate the wave function with this j minus, what it does is, it gives us the wave function with m value reduced by 1 multiplied with its eigenvalue, that is this. So this is the eigenvalue. So once this j minus operator operates on the wave function, it would give the wave function with m value less than 1 multiplied with this eigenvalue, root over j plus m into j minus m plus 1 h cut. So h cut is taken as 1 unit here. So that is the thing we need to find out now. So here in what we have to do is, we need to operate this equation, operating with j minus on both sides of this equation. So j minus 5 of 3 by 2 comma 3 by 2, and j minus is nothing but j1 minus j2 minus in uncoupled form. So because this is uncoupled form, so j1 minus plus j2 minus psi of 1 comma half. Now if we apply this formula, so here j minus is operating on this. So this is j and this is m. In the notation also we have represented phi of j comma m. So what this j minus would do is reduce the value of m by 1. So 3 by 2 minus 1. 3 by 2 minus 1 with multiply with its eigenvalue. So in the place of j here we are having 3 by 2, in the place of m 3 by 2. So j plus m 3 by 2 plus 3 by 2, j minus m 3 by 2 minus 3 by 2 plus 1. So this one would get cancelled, here we would have 1, and 3 by 2 plus 3 by 2 is nothing but 6 by 2, that is 3, root 3 into 1. So phi of here m value is being reduced by 1. And here on the right hand side, this is where the confusion starts, because here already we are having here jm. So we just need to take this into account, these two quantities. But here, so first of all, this is also a plus b into c. So there is nothing but ac plus bc. So this is operating on this one, and this is operating plus this on operating on this one. Next is j1 minus would only reduce the value of m1. It would not reduce the value of m2. As in the notation we have found, this is not j1 m1, or neither this is j2 m2. This is m1 comma m2. So j1 minus would reduce the value of m1 by 1. So 1 minus 1, and m2 would remain the same. And next thing is, here j1 is given in the question, that is 1. That is this term, j1 plus m1, square root of j1 plus m1 into j1 minus m1 plus 1. That is the thing. So j1 in the place of j1, it is given in the question. Actually this is m1 and this is m2. This is m1, this is m2. But this is j, this is m. So if we want jm values, we can find within this only on the left hand side. But on the right hand side, one of the thing is given in the question and one of the thing would remain here. So j1 is 1 and m1 is 1. So j1 minus m1, 1 minus 1 plus 1 square root. And next thing is j2 minus operating on this wave function. So it would reduce the value of m2. It would not do anything with m1. So psi of 1 half minus 1. and here as we know j2 is half, so half m2 is also half, so half plus half and j2 minus m2, half minus half plus 1. So if we solve it, so 1 plus 1 2, 1 minus 1 plus 1 1 root 2, and 1 minus 1 0 half, and here half plus half 1, half minus half would give answer 1, so overall you would have 1. So 1 comma um, plus xi of 1 comma minus half. So next thing is we need to send this root 3 that side. So here it is multiply, here it would divide. So phi of 3 by 2 comma half is another root 2 by root 3 xi of 0 comma half, and here 1 by root 3 xi of 1 comma minus half. So finally we would have this equation. Under this case, equation 1 is expressed as. So each of the equations has to be expressed of the form as this form. So phi of j comma m summation Clebsch Gordan coefficient multiplied with uncoupled form, like that. So phi of 3 by 2 comma half can be represented as, so here in the place xi of 0 comma half, here xi of 1 comma minus half, and next thing is 0 comma half is being converted to 3 by 2 comma half. So 0 comma half getting converted to 3 by 2 comma half, and here 1 comma minus half is being converted to 3 by 2 comma half. So 1 comma minus half being converted to 3 by 2 comma half. So that is the meaning of this Clebsch Gordan coefficients. So the if we express in the form of equation 1, now we need to comparing equation 8 and 9. So comparing equation 8 and 9, we would get another Clebsch Gordan coefficients has. So this is the Clebsch Gordan coefficient. So in the place of this, we are having root 2 by 3. So root 2 by 3. And in the place of this, bra 1 comma minus half, 3 by 2 comma half get. So in the place of this, we are having 1 by root 3. So 1 by root 3. So we have found another set of Clebsch Gordan coefficients. And next, another again what we need to do is applying lowering operator again to equation 8 we get. So to this equation we need to apply again the same procedure, applying the same formulas, and again we need to apply j minus. So we would get this term phi of 3 by 2 comma minus half 1 by root 3 xi of minus 1 comma half plus root 2 by 3 xi of 0 comma minus half. This is possible from if we consider the formulas. So actually here what it is, so every equation has to be written in this form, in this summation form. So here xi of minus 1 comma half is being converted to 3 by 2 comma minus half. So minus 1 comma half converted to 3 by 2 comma minus half, and here also 0 comma minus half being converted to 3 by 2 comma minus half, 0 comma minus half being converted to 3 by 2 comma minus half. So this in this way we can express. So how we are getting this equation? By applying j minus to equation 8. That solvation let us see in the note. So this is the equation 8. So phi of 3 by 2 comma half, phi of 3 by 2 comma half, xi root 2 by 3, xi of 0 comma half, 1 by root 3, 1 minus half. So on both sides of this equation we need to apply j minus. So j minus phi of 3 by 2 comma half, and j minus j1 minus plus j2 minus. So this entire thing, so root 2 by 3. So now let's see how to solve this. So applying again the same formula, root of j plus m, j minus m plus 1. So in the here we are having j value 3 by 2 and m value half, 3 by 2 plus half and 3 by 2 minus half, j minus m, and plus 1. It would reduce the value of m by 1. So half minus 1, you would have minus half. So that is the thing. And on the right hand side we need to consider. So if we consider first operating j1 minus, so this is of the form a plus b into c plus d. So we would have 4 possible terms, a plus b into c plus d, ac plus ad, bc plus bd, like that 4 possible terms. So let's see first term. So j1 minus operating on this. So 1 by root 2 by 3 taken aside. So 0 half. So j1 minus would only reduce the value of m1. So here this is m1 and this is m2. Xi of m1 0 minus 1, m2 would remain the same half, and we know that j1 plus m1 root over j1 plus m1 into j1 minus m1 plus 1. So j1 is already given in the question. This is not j1 here. This is where the confusion arises. This is j, this is m, but here this is m1, this is m2, this is m1, this is m2. So in the question already it is given that j1 is 1, so 1, and m1 here is 0, so 1 plus 0, and 1 minus 0 plus 1. And next thing is operating j2 minus on this term. So j2 minus would only reduce the value of m2 by 1. It would not reduce the value of m1. So 0, m1 0, and half minus 1, half minus 1. And here in this case j2 is, as we are considering j2 m2, j2 is half as given in the question, and m2 is also half for this wave function. So half plus half, and j2 minus m2, half minus half plus 1. So this is the possible case. And next thing is operating j1 minus on this. So it would reduce here for this wave function m1 is 1 and m2 is minus half, different from here. So m1 reduced by 1, 1 minus 1, and minus half would remain the same. And as we know, j1 as it is given in the question 1, so root of j1 plus m1, m1 here is 1, so 1 plus 1. So j1 minus m1, 1 minus 1 plus 1. And next thing is j2 minus operating on this. So j2 minus would reduce the value of m2. So m2 minus half is there. Minus half minus 1 is nothing but minus 3 by 2. But m2 equals to minus 3 by 2 term is not there. So we are only having m1 has 1 0 minus 1 and m2 has half comma minus half. So beyond that we cannot have 3 by 2 minus 3 by 2 like that. Hence we are not having fourth term. So because minus 3 by 2 is not there for the m2. So if you operate this term on this, it would vanish, as just we have discussed in the generating functions formula equations. So at that time wave function would get vanished for the maximum minimum possible value. So minus half minus 1 minus 3 by 2, that value is not there for m2. Only m2 has half comma minus half, and m1 has 1 0 0 0 minus 1 1. So that term is neglected. So now if we do simplification, so 3 by 2 plus half is 4 by 2 2. So 3 by 2 minus 1 half 1, 1 plus 1 2. So root 2 into root 2 we would have here. And next here half minus 1 minus half, and here if we consider root 2 by 3, 1 plus 0 1, 1 minus 0 plus 1 root 2 for this, and minus 0 minus 1 minus half half, and here half plus half 1, and half minus half 0 plus 1. So we would have only 1. So root 2 by 3 xi of 0 comma minus half, and here 1 by root 3, 1 plus 1 is 2, 1 minus 1 would get cancelled 1. So root 2 by 3 0 xi of 1 minus 1 is 0 minus half, like that. So after simplification, so now what we can do is cancelling 2 on both sides, that is root 2 into root 2. So root 2 cancel, root 2 cancel. Here only one of the root 2 would get cancelled. Another root 2 would be divided. That means what we have to do is dividing the entire equation by 2, because root 2 into root 2 is 2. So if we divide the entire equation by 2, 2 would get cancelled, 2 would get cancelled, 1 by root 3 would be remaining here. Root 2 by 2, that is root 2. Root 2 by 2 is nothing but 1 by root 2. And here also root 2 by 2 is nothing but 1 by root 2. So we would have 1 by root 6, 1 by root 6, like that. And this is, next thing is, so this is nothing but these both are same, just like a plus a. So 1 by root 2 root 3 root 3 root 2 xi of 0 comma minus half, xi of 0 comma minus half. So that is number 2 by root 3 by root 3 into root 2. So 2 by root 2 is nothing but root 2. So root 2 by 3, xi of 0 comma minus half. So on. This is the possible simplification. So finally we would have this. So that is the simplification of this term. So comparing 11 and 12, we get Clebsch Gordan coefficients. So we need to compare this both. So every equation has to be expressed in the form of equation 1. So if we compare, in the place of this we are having 1 by root 3, and in the place of this 0 minus half, 3 by 2 minus half, we are having this root 2 by 3. So we have found another set of Clebsch Gordan coefficients. Now, and next thing is, again we need to apply lowering operator. So applying lowering operator again to equation 1 we get. So equation 11. So this is the equation 11. So what are all the result of we are getting? So again to the result we need to apply in the same manner this j minus. So to this equation we are applying. So j minus 5 of 3 by 2 minus half, j minus 5 of 3 by 2 minus half, and j1 minus and j2 minus this entire equation 1 by root 3, 1 by root 3 xi of 0 minus half, xi of minus 1 comma half, and root 2 by 3 xi of 0 comma minus half. So if we apply and simplify, we would get this equation. So how we are getting that one we would see now. So this is the operation. This is equation 11 and we are operating j minus on both sides. Now if we consider on the left hand side, so here j is 3 by 2, m is minus half. So when j minus is operating on the wave function, it would reduce the value of m by 1. So minus half minus 1, minus half minus 1, j is 3 by 2. So root of j plus m into j minus m plus 1, that is the eigenvalue. So here j is 3 by 2 and m is minus half. So j plus m, and j minus m is 3 by 2 minus of minus 1 by 2, that is plus 1 by 2 plus 1. And on the right hand side if we see, so here where the confusion arises, as I said, so first of all, so here also we would have 4 terms. It is of the form a plus b into c plus d. So 4 terms. So first j1 minus operating on this equation. So if we consider this, what does the j1 minus do? It would reduce the value of m by 1, m1. So this is m1. For this wave function, m1 is minus 1 and m2 is half. And for this wave function, m1 is 0 and m2 is minus half. So if we operate j1 minus on this, it would reduce m1 by 1, minus 1 minus 1, that is minus 2. But m1 value minus 2 is not possible because it is only from minus 1, 0, 1. So it is only minus 1, 0, 1 m1 value. I cannot have minus 2. Hence j1 minus operating on this is not allowed. So minus 2 is not there for m1. Now if we see apply j2 minus on this, so it would reduce m2 by 1, half minus 1. So half minus 1, m1 would remain the same, and square root of j2 plus m2. j2 is given in the question, that is half. j1 is 1 and j2 is half. We are finding the Clebsch Gordan coefficients for these values only. So j2 is half and m2 is half for this wave function. So j2 plus m2 and j2 minus m2, half minus half plus 1. And 1 by root 3 is there, and again operating j1 minus on this equation. So it would reduce the value of m1 by 1. So 0 minus 1, which is allowed, and m2 would remain the same, minus half. And here j1 is 1 given in the question and m1 is 0. So j1 plus m1, square root of j1 plus m1, 1 plus 0, and j into j1 minus m1 plus 1, 1 minus 0 plus 1, as j is 1 and m is 0. j1 given in the question 1 and m1 here is 0. So this is a possible case. And next we cannot operate j2 minus on this because j2 minus would reduce the value of m2 by 1. Minus half minus 1 is minus 3 by 2. So m2 is, we have only m2 is equals half comma minus half. Minus 3 by 2 is not possible. So remaining 2 terms would get neglected. So now if we simplify, 3 by 2 minus half is nothing but 1. 3 by 2 plus half, that is 2. 2 plus 1, root 3. 1 into 3, root 3. So this is the term, and here half plus half is 1. Half minus half would get cancelled, 1, root 1. We would have 1 by root 3, xi of minus 1, half comma minus half. Half comma minus half is minus half. Here also minus half comma minus 1 is minus 3 by 2. And here if we see, 0 minus 1 minus 1 minus half would remain the same, and 1 plus 0 1 minus 0 plus 1 is root 2. So root 2 we would have root 2 by 3 root into root 2. And next thing is root 2 into root 2 is 2. So here we are having 1 by root 3 this term, and here 2 by root 3 is same. These both are same. So this is like a plus 2a, that is nothing but 3a. So we are having 3 by root 3 into this term, minus 1 minus half. And next thing is root 3 into root 3 would get cancelled, because 3 is root 3 whole square, and this root 3 would get cancelled. Finally we would have this term. Hence we are having, after application of j minus, this term. So this is the simplification. So under this condition, equation, so if we express this one in the form of equation 1, so here minus 1 minus half is being converted to 3 by 2 comma minus 3 by 2. So minus 1 minus half getting converted to 3 by 2 comma minus 3 by 2. So psi of minus 1 minus half, phi of 3 by 2 minus 3 by 2. So this is the form of equation 1. So if we compare these both equations, so in the place of this we are having 1. In the place of this Clebsch Gordan coefficient we are having 1. If we compare these two equations, like that is 14. So 14 is same as this equation. So if we compare these two equations, we are having Clebsch Gordan coefficient 1. So we have found out. So no further we cannot operate j minus, because if we operate it would reduce minus 3 by 2 minus 1, that is minus 5 by 2, but m value minus 5 by 2 is not possible. So as we have discussed here, so m values is 3 by 2, half minus 3 by 2, and half comma minus half for j equals 3 by 2, and this is for j equals 1 by 2. So we don't have minus 5 by 2. So again we no need to apply j minus, but still we need to find out some of the Clebsch Gordan coefficients. So in order to find the remaining Clebsch Gordan coefficients, and as we cannot further apply j minus, so we need to use the help of orthonormality condition. So here now to find remaining 4 Clebsch Gordan coefficients, we are using orthonormality condition. So keeping in mind that orthonormal linear combination decreases the value of j by 1, the orthonormal linear combination of equation 8 is. So orthonormality, as we know that integration of phi into phi star, that is integration of psi I psi j star d tau equals to 1 when I equals to j, equals to 0 when I is not equals to j. So like that orthonormality condition. So here what they are saying is it reduces the value of j by 1. So they are saying for equation 8. So this is the equation 8. So for this equation 8, if we reduce, this is j value 3 by 2 and this is m value. If we reduce j value by 1, 3 by 2 minus 1 is nothing but half. And m value we are not changing. So if this is the wave function having j value half, and this is the wave function having j value 3 by 2. So they are two different wave functions. So then orthonormality condition arises. How? I means integration of phi into this phi star d tau equals to 0 we should get. This is possible only if right hand side is 0. This could be made 0. So here what we are having, psi of 0 comma half. Here also psi of 0 comma half. Here psi of 1 comma minus half. And here also psi of 1 comma minus half. But only thing is here root 2 by 3. Here minus 1 by root 3. So if we multiply them both, what we would get is minus root 2 by 3. And here root 2 by 3, here 1 by root 3. So if we multiply therefore root 2 by 3. So minus root 2 by 3 plus root 2 by 3, that is equals to 0. Hence, based on the orthonormality condition, we are having this equation. So it reduces the value of j by 1. So 3 by 2 by minus 1 is half. And these coefficients multiplied together, we should get 0. These are the same, and this coefficients of 2 by 3 minus 1 by root 3. Why we are taking minus here means so that we can get cancellation takes place finally, so that integration phi j, that is integration of phi phi j phi I star theta equals to 0 based in order to satisfy that orthonormality condition. Hence we are having here minus 1 by root 3. So that is the case. And under this condition, equation 1 expressed as. So if we express this in the form of equation 1, so 0 comma half getting converted to half comma half, 0 comma half, half comma half, and 1 comma minus half getting converted to half comma half, 1 comma minus half getting converted to half comma half. So if we express in the form of equation 1, summation transformation equation, so comparing 17 and 18, so this both equation. So in the place of this we are having minus 1 by root 3, so minus 1 by root 3, and in the place of this we are having root 2 by 3, so root 2 by 3. So these are the another set of Clebsch Gordan coefficients. And next thing is the orthonormal linear combination to equation 11. In the same manner for this equation 11, this is the equation 11, we are having another orthonormal linear combination. So here j value we are having 3 by 2. So 3 by 2 minus 1 is nothing but half, and minus half would remain the same. Here xi of minus 1 comma half, xi of minus 1 comma half, xi of 0 comma minus half, xi of 0 comma minus half will remain the same. Now we need to consider the coefficients. So here 1 by root 3 into minus 2 by root 3 minus root over 2 by 3. So if we multiply they both, that is integration phi into phi star theta must be equal to 0. So this one multiplied with this, so phi of minus 1 half, here also xi of minus 1 comma half. So this coefficient multiplied with this corresponding coefficient, that is we would get minus root 2 by 3, and here root 2 by 3 is there, here 1 by root 3, that is root 2 by 3 plus root 2 by 3. So minus root 2 by 3 plus root 2, minus root 2 by 3 plus root 2 by 3. So both of them would get cancelled, we would get 0 based on this orthonormality condition which we should satisfy. So this corresponding coefficients, if they get multiplied, they added up and it would give us 0. Should give us 0. So in such a manner these coefficients has to be decided. If we keep plus here, then they won't get cancelled. So what we would get is root 2 by 3 plus root 2 by 3, that is 2 root 2 by 3. So in order to avoid that addition, in order to get 0, here minus sign should be there, like that. So under this condition equation 1 would be, so if we express this equation, so this is the appropriate orthonormal equation for this equation. So if we multiply this both equation and integrate over theta, we will get 0. This is the orthonormality condition. And if we express this equation in the form of equation 1, so this minus 1 comma half getting converted to half comma minus half, minus 1 comma half, half comma minus half, 0 comma minus half getting converted to half comma minus half, minus half getting converted to half comma minus half. So this is the possible expression. So if we compare this 20 and 21, so in the place of this we are having minus root 2 by 3, and in the place of this 1 by root 3. So these are all the complete analysis of 7, 10, 13, 16, 19, 22. So this 22, this 19, all these are all Clebsch Gordan coefficient equations. Express require non-vanishing Clebsch Gordan coefficients. As discussed in the earlier case, these are non-vanishing. So for the p state of an electron, so remaining Clebsch Gordan coefficients are all 0. So the matrix representing this Clebsch Gordan coefficient may be expressed as. So this is the matrix for the Clebsch Gordan coefficient. So this is the matrix representation. So how to represent is, so here we have to take Jm values. So what are all the J values we are having? 3 by 2, 3 by 2, 3 by 2, 3 by 2. Corresponding M values plus 3 by 2, half, minus 3 by 2. And again J value we are having half comma half. Corresponding M values are half comma minus half. So this is Jm, that is coupled form. And in the uncoupled form we are having these many possibilities. One, that is xi value, M values minus 1, 0, 1. And corresponding M2 values half minus half, half minus half, half minus half. So now this matrix, how to represent this matrix. So this is this Clebsch Gordan coefficient matrix. This form is being converted to this form. So now how to write this matrix is, so phi of 3 by 2 comma 3 by 2, if you consider that equation, so phi of 3 by 2 comma 3 by 2, xi of 1 comma half, and remaining terms are all 0, coefficients are all 0 if you consider. So phi of 3 by 2 comma 3 by 2, 1 into xi of 1 comma half. So phi of 3 by 2 comma 3 by 2, 1 into xi of 1 comma half. Remaining are all 0. And next if we consider 3 by 2, phi of 3 by 2 comma half. So phi of 3 by 2 comma half. So this is phi of 3 by 2 comma half. So xi of 0 comma half, xi of 1 comma minus half. So xi of 0 comma half, xi of 1 comma minus half. So at xi of 0 comma half, root 2 by 3. Xi of 0 comma half, root 2 by 3. And xi of 1 comma minus half, 1 by root 3. Xi of 1 comma minus half, 1 by root 3. So in this manner. So remaining terms are all 0. We don't have remaining terms. So in the similar manner for this phi of j comma m also the same. So phi of j comma m, half comma half. So xi of 0 comma half minus 1 by root 3. So xi of 0 comma half. So this is minus 1 by root 3. And xi of 1 comma minus half, root 2 by 3. Xi of 1 comma minus half, root 2 by 3. So in this form can represent. And also if we observe from here, so when m is equals to m1 plus m2, that is, what is here m? In this case if we consider, what is m1 plus m2, 1 plus half is 3 by 2. So when m is 3 by 2, m1 plus m2, so in that case we are having 1. So remaining all cases it is 0. In the same manner, in the next case if we consider, m is equals to m1 plus m2, m is half, that means 1 minus half is half. So we are having Clebsch Gordan coefficient, non-vanishing Clebsch Gordan coefficient. And here also 0 plus half is half. Here also we are having non-vanishing Clebsch Gordan coefficient. So this is the meaning of this equation. So when m is equals to m1 plus m2, we have non-vanishing Clebsch Gordan coefficient. That is, this is not equal to 0. And when m is not equal to this, then the Clebsch, in that case, Clebsch Gordan coefficients are all 0. So that is the meaning. And here also if we see, so when m is minus half, so it is possible when 0 minus half, and minus 1 plus half, minus half. So in this case, we are having non-vanishing Clebsch Gordan coefficient. Here also minus 3 by 2. So minus 1 minus half, minus 3 by 2. Hence we are having non-vanishing Clebsch Gordan coefficient. So these are the non-vanishing Clebsch Gordan coefficients when m is equals to m1 plus m2. So this is the form, required form, matrix form. So by the help of this matrix, we may represent the transformation equation from uncoupled to coupled representation by matrix equation as. So this is uncoupled form. This form is getting transformed to this coupled form with the help of this transformation matrix. So this is the transformation matrix with the help of this Clebsch Gordan coefficients. So here if we see phi of 3 by 2 comma 3 by 2, that is 1 into xi of 1 comma half. So that is the equation, phi of 3 by 2 xi of 1 comma half. And phi of 3 by 2 comma half. So phi of 3 by 2 comma half, this is phi of 3 by 2 comma half. So xi of 0 comma 1 by 2. And xi of 1 comma minus half. So xi of 1 comma minus half, and that is 1 by root 3, and xi of 0 comma half, root 2 by 3. So this is nothing but expressing these equations. So these equations in the matrix form. This is the matrix form of those equations. So thus this uncoupled form is being converted to coupled form, by multiplying with this matrix, transformation matrix. So this is the Clebsch Gordan coefficient matrix. So these are all the Clebsch Gordan coefficient for J1 is equals to 1 and J2 is equals to half. So here we are having 6 rows, 1, 2, 3, 4, 5, 6 rows, 1 column, and this is 6 rows, 6 columns, and 6 rows, 1 column. So this is the representation. So that is the Clebsch Gordan coefficient calculation for J1 is equals to 1 and J2 is equals to half. So thank you.